I basically read some very pessimistic arguments that we will never be able to test quantum gravity effects because that will be basically probing the beginning of the universe. Since then, there's been a kind of a guarded optimism in this community that might be some room for phenomenology. And I even read in a paper of one of the panel members here that he urged theorists to come with predictions in order not to lag behind the phenomena when they will come, the data will come. Because, according to some philosophers of science, lagging behind the phenomena is a sign of a degenerate research program. So basically, the idea is that we need to come up with predictions of the quantum gravity scenarios that can be fit to data. Lacking that data, what you are maybe left with is thought experiments that you can perform. They are cheaper, I guess, and they have a very basic role in the development of physics. So, starting with even with Aristotle, that tried to speculate about the infinity or finiteness of the universe using very simple thought experiments, going to much more famous one like Galileo's falling bodies experiment and Newton's bucket and the two spheres, which were contrasted by Mach contra-thought experiments. Mach, by the way, was one of the most strong, although he was an empiricist, a strict empiricist, he was a very in support of thought experiments as developing physics, in contrast to another empiricist in the history of science named Pierre Duhem that thought that thought experiments had no place in science because they are purely a priori, purely involve armchair philosophy or armchair physics and have nothing to do with the natural world. Later thought experiments, famous ones are, of course, Einstein chasing after the photon thought experiment that led to the conception of special relativity, and the elevator thought experiment that led to the equivalence principle, and EPR, famous thought experiments that was finally even translated to a real experiment aspect type experiment in the 80s, and Schrödinger cat experiment that we all love to hate. So there are all these thought experiments in the development of physics, and the question, or 5 questions I thought might be interesting to ask in this setup for the panelists and also for you, and I was warned that giving physicists all the questions at once is a dangerous thing, because then, everybody, they are not disciplined as philosophers, but I will try because I think we don't have a lot of time and people are tired. So these are, I think, what I hope to ask. And if you have other questions, and maybe panelists have other questions, I'd be happy to consider them. The first question is something that, as I said, came up in the discussion of philosophers about the role of thought experiments in science. Since thought experiments don't involve any contact with reality or with the experimental world, now, do they pose a threat to the idea that philosophers might have that all knowledge comes from experience? And in a kind of a counter question to that is, if they are really detached from the empirical world, how much they can advance our knowledge of the world? Can we learn new things from thought experiments, although we don't come to contact with the world performing that, just an exercise of the mind? Another question related to that is that some thought experiments, notably the EPR one, were translated into a real one, but some thought experiments may never be, in principle, translated into a real setup. So how are we going to think about them in that context? If we think about physical theory being testable in principle, that's the mark or the sign of a scientific theory, at least according to some, then, if you are proposing a thought experiment to test a certain theory, and that thought experiment can never be made, then how severe a test is this? Fourth question, what is the role of thought experiments in theoretical physics, and in particular in quantum gravity? And here, again, a little bit of background. In philosophy of science, we have 2 contexts which were famously popularized by a guy named Hans Reichenbach. You might have heard of him. One is the context of justification, where you think about the physical theory as laid out, and then what the philosopher does is just looking at the interpretation of the theory or the epistemic status of the theory. Why should I believe the theory? What does it say about the world? That's what philosophers do. There is another context, the context of discovery, which is basically how physicists, theoretical physicists, come up with a theory. And according to Reichenbach, that's something that philosophers need not discuss, because that has sociological factors, psychological factors. And now, in the case of quantum gravity, where you don't have any theory yet to propose to us, philosophers, what we are left is this context of theoretical practice, which for me, personally, is very interesting. So I would really like to know what you think about what is the role of those thought experiments in the actual, or coming up with a theory. For example, in DSR or in theory which are theories which are not yet mature. Do they play any role? And the last question is, how much consistency and rigor should we incorporate into thought experiments, given that we are not going to perform them anyway? So should we be rigorous and consistent in our thinking, or just, play the game in a different way? So, I don't have any, I didn't think about any specific way of doing that. Maybe, one of you thinks is prepared to answer one, two, or all the questions can start.
Right, so why don't I just start? So I think I will take the first two questions together since they are kind of related. So about whether or not thought experiments are sophisticated, I think sophisticated is an observer-dependent statement. So my work is always the most sophisticated one. So I don't really have a lot to say about this. But about knowledge coming from experience, I think there are very many sorts of experience. I mean, certainly going out and taking data and collecting it is a sort of experience, which is what we probably have in mind. But that's not the only thing we have. We also have experience on the most trivial level that mathematics works very well. And on a more sophisticated level, we know there are certain procedures that we use that work very well. Take something like gauge invariance, symmetries more generally, the Lagrangian principle, and so on and so forth. And that's certainly also a kind of experience. And people use these for their theories. So I certainly don't think that all knowledge comes from observation, but it's also knowledge about the procedures that you use, and you learn to rely on them. So maybe that becomes clearer when I give you a rough picture how I like to think about knowledge that's growing. So you can picture this as some kind of a map, maybe, where knowledge sits. So that's stuff that we believe we know, and certainly there's nothing that we know to 100% certainty, but there's always a slight chance that it might turn out that all of our observations have been wrong. But certainly there's some kind of knowledge that is very, very, very unlikely to ever be wrong. And what we want to do in science is that we want to expand this knowledge. So it's like you have some little islands, maybe they might not all be connected, and you want to go beyond that. And now the question is, how do you do this? Well, the one thing is that you make an experiment. So you basically go somewhere into the unknown and you just measure something. So that's the one thing that you can do. But then there's the question, where do you measure? Right? There's a lot of unknown stuff. There are the obvious things to look at it, and Klaus mentioned this yesterday in his introduction to the discussion. You go to higher energies, you go to larger distances, you go to smaller distances, you go to higher acceleration, and so on and so forth. So this is all the unknown, basically, that you want to discover. But what you also need in most cases is that you need a theorist to make a good guess where there's an interesting place to look. And so for this to be reliable, what you have to take into account to a large degree is mathematical consistency. And you really have to understand your theories, and you have to know how to interpret them, and so on and so forth. And in that process, thought experiments are tremendously helpful. So that's roughly what I think thought experiments are good for. They give you a better grip on your mathematical apparatus, which might be very abstract. So you know better how to understand it.
But still, this might be just an intuition pumping machinery. So you get a better grip on your intuition, you sharpen your intuition. But the worry of the empiricist is that why should you? So you say, I trust my intuition. There is some intuition that are never wrong, they are a priori true. Okay, why would they apply to nature?
Well, I'm not good with the isms, so...
let me, I think I agree with what Sabina said, but I would just put slightly different language. I mean, you have the word, what philosophers call strict empirism. In my personal opinion, strict empiricism is simply false. So, as Sabina said, you have data and you have interpretation. So data by themselves, if I give you a bunch of data, it means absolutely nothing. And the interpretation comes not just by a person interpreting something, but what theoretical structure that we have within which the data is being collected, and how this theoretical structure is viewed at the present time, and lots of other things come into picture in the interpretation of that data. So empiricism, yes, but strict, it depends on what you mean by the strict empirism. So,
Well, can I just say something which is probably an example of this? So, I've been involved, throughout the years with something called varying constants, and the problem there is immediately how do you measure these things? And quite often the procedure is such that the constancy of the quantities is folded in the measurement. So, for example, if you define your unit of time from a given transition, and then unit of distance, like the distance traveled by light at that period. Of course, the speed of light can't change, because by definition, it's like 1 light year per year, right? That's what basically you say. Of course, in that point, the experimentalist is not measuring anything. The experimentalist in that stage is actually, it's collecting data which is tautological, in a way. And you actually need the full theory and the full picture to be able to interpret this body of observations. And sometimes, so there's actually a very interesting discussion between Mach and Poincaré about this, because they have completely different views. So there's the very, the strongly empiricist view, which is everything is experiment of Mach, and the point of view of Poincaré, which in fact they are definitions folded into the experiments, and the definitions are the role of the theories. At the same time, they have to be made to simplify the picture. For example, the law of inertia is totally tautological, yet it's the simplest way to actually
Again, yes.
Well, rather interesting that it seems to me the best thought experiments are those that have ambiguous interpretation. And let me give 2 examples. So there are actually 2 thought experiments that we knew when we talked about Galileo's doing driving something, watching it fall. But so the simplest one is just the observation that if you drop something from the top of a tower, it falls to the base of the tower. The tower experiment. And this was interpreted by Galileo as an argument for the principle of inertia. That is, the Earth is moving, but the object has inertia when it's on the top of the tower. When you let it go, and its inertia carries it, so as the tower is moving with the Earth, it falls to the bottom of the tower. But of course, the Aristotelians, with a different physics, interpreted the very same thought experiment and even experiment as proof of the stationary, that the Earth was stationary, not moving. And similarly, or a case which is somewhat similar, is Einstein's Hall argument. There were 2 versions of the Hall argument. The first version of the Hall argument was used by Einstein to declare that general relativity, that the right theory of gravity could not be diffeomorphism invariant. And he believed that for a few years. And then a friend of his turned him around and proposed that the right interpretation of the Hall argument was that diffeomorphisms had to relate physically, had to be that physical histories of the universe had to correspond to diffeomorphism classes rather than individual metrics and geometries. And on these thought experiments with ambiguous or even opposite interpretations,
Also Newton's bucket with Mach response, I think.
yeah, what they really are is they create a conversation space on which you can change your mind.
Don't these three, Newton and Galileo and Einstein, I mean, these were not only thought experimentalists, they were real experimentalists. Galileo was a tinkerer, Newton obviously was, and Einstein held, in addition to being a patent examiner, he had several patents. Sometimes the connection between actual experiments, I think, would be beneficial.
Yeah, and just to comment on that, there's a very interesting book by I forget, Peter, somebody, a historian of science, Peter Galison, about Einstein and Poincaré. And the whole thing that I was doing with establishing coordinates by exchanging light signals was actually the practice of the time in the world of telegraphs. That is, in the actual synchronization of time zones and clocks around the planet Earth was being done at that time by exchanges of telegraph signals. And both Poincaré, in one of his jobs, I forget, but he was deeply involved in the practical aspects of that. And Einstein, as a patent examiner, examined a number of patents that were directed to establishing synchronization of clocks through exchange of signals. So the thing that we learn now is, if it is a thought experiment, was actually not just experiment, but engineering practice of that time.
It's a related point. I mean, actually not related, maybe complementary point, is that you talk about ambiguity in the thought experiment, but another function of a thought experiment is to push the limit of what is not achievable in the real practice. John Locke, a philosopher, once said that if you want to really understand something, push it to the limit where it is an extreme limit, and then you really learn about it. And that's where the function of thought experiment comes in, because in real experiments you sometimes cannot achieve that. So to answer, or at least give my opinion of the first 2 points, is that it may, the strict empiricism may be limited, but the function of thought experiments is go beyond that, and you do learn something about nature by doing so. It doesn't have to be it doesn't have to be just derived from the experiment.
As a philosopher, I'd be all for physicists to be less empiricist and more, Platonist or rational.
Philosophical.
Oh yeah, but that strikes me as really weird, in a sense that again there seems to be a very strong tension between cooking up some scenario which is completely far-fetched and based on some consistency of mathematical principles that maybe you get the connection to the real world because you actually verify these principles in many experiments. So you basically trust these principles, and then extrapolating from those principles to other scenarios when you never tested the theory and put constraints on that theory. How can you be sure that those principles will be still valid in those domains you haven't tested? So that, to me, that's...
I think that it's important to distinguish the role of testing the theory and testing nature. By thought experiments, you test your theory. You subject your theory to self-consistency internal tests. And something very different is to test nature. When your theory, which you believe to be correct, shows perhaps some internal self-consistency and there are alternative paths that are open to you to resolve it, then perhaps the only way to resolve it is to look at nature. So we should never confuse testing nature and testing theory.
Well, I guess you test nature by testing your theories. There is no other way to test nature.
You can test your theory by testing its internal self-consistency independent of its nature.
Independent of its
independent of nature, independent of whether it applies to nature or not, the theory may be internally self-consistent or not.
I think that kind of brings us to the third question. So the question, if you're thinking about a thought experiment in your theory that you cannot possibly ever realize, what's it good for?
Well, either your theory itself, if it's supposed to be a complete theory of nature, which you are supposed to believe, should tell you that this experiment is impossible to ever realize. And then you are safe, right? If I'm testing quantum mechanics and I know that my theory itself is telling me I cannot localize a particle with more than 3, then this is a waste of time because I'm violating the postulates of the theory. But if you want to know your theory is internally self-consistent, it's fine to realize experiments that you may never realize. You have already detected that the theory is internally self-consistent, you see, because it allows you to construct a scenario to which the theory has no reasonable answer. That tells you the theory internally has a problem. And you should better look for a better theory. Because this, for certainly, cannot be nature.
There's a famous historical example of that. It is that of the debate between Einstein and Bohr about the internal consistency of quantum mechanics. While Einstein wanted to show that it is possible to measure simultaneously, for example, position and momentum, and then show that the Heisenberg principle was avoidable.
Well,
and
then,
was the yes, and then Bohr tried to think of a way why, even thinking how the proposed experiment by Einstein, that maybe it couldn't be realized in practice, but maybe by which principle it should work. And then this gave him an answer of, so in this case, for example, I think I agree with Daniel, the internal consistency of the theory can be tested just by poorly thought experiments.
Yeah, what I was trying to say was more like, consider you have a theory that is not internally consistent, but you have no way to ever test the inconsistency. I mean, maybe a good example of this thing when talking about quantum gravity is, I believe, what led Freeman Dyson to think that quantum field theory and classical general relativity can kind of peacefully coexist, is that there's so far no experiment that was done sometime in the 90s or something that could actually test that potential disagreement. I mean, there are thought experiments, like you could try to measure a photon effect for a graviton or something, and then you try to figure out how the detector would have, how large would it have to be, and how long would you have to measure to measure a single stupid graviton, and you end up with things like the size of the Jupiter, and you have to measure, I don't know, 100 times the lifetimes of the universe or something. So, is that a realistic experiment? Do we have to worry about this?
If there was if you had a theory of quantum gravity, and it gave you, computing in 2 different ways, different answers for the same thing, I would say this theory is not good.
But if you can never test the disagreement.
No, but you know the theory is not good because it's internally self-contradictory. Once you allow one internal self-contradiction, once you allow any postulate to be truth and false at the same time, you can conclude anything from the theory.
But this is not about quote.
No, yes, it's about if you have a theory that is internally self-contradictory.
That's the theoretical structure you're testing.
Yes, of course, you're testing your theory with the thought. That's what I said. You're subjecting your theory to the stress of pushing it to the limit that you're talking with a thought experiment.
Historically.
So your theory should either prevent that thought experiment from being done, so the experiment should be impossible by the rules of this theory, or should give a consistent answer.
Yeah, I want to try to puncture some of the assumptions we made. So one of them is this thing about what does it mean to not be able to do an experiment. So for example, what about arguments in which the only way in which they can't be done is that we would need to be far in the future. So by this I mean
infinity anymore.
Yeah. So I mean, for example, the doomsday argument or the Boltzmann-Brain argument. Okay. And the doomsday argument is an argument several people claim it's invented. So the argument goes the following way: I am a typical person. Thereby, I should be typical in any ensemble that you can name. That is, I should be a typical member. It's especially funny when Hogan Nielsen starts. But I can try for it. So I am a typical person. I should be typical in any ensemble any reasonable ensemble that can be specified. So let us consider the ensemble of all human beings who will ever live. Unless you're insane like me you're a presentist like me, that you would say that makes sense. Okay, that is the ensemble of all human beings who will ever live. There must be such an ensemble. Okay? Now, if I'm a typical member of it, then it means that I'm typical in every domain in many different ways. And one way in which I will be typical is birth order. So I'm very unlikely to be one of the very earliest of all the human beings who ever lived, and very unlikely to be one of the last. So therefore, I must have been born in the middle, roughly, up to an order of magnitude. So there must be up to an order of magnitude roughly the same number of people coming after me as have already lived. And since the population has been growing exponentially, the only way that can be true is that the population plunges exponentially within my lifetime. And several people have published this, including a book by a professor of philosophy. An astronomer at Princeton published, I forget the name, published this in Nature. Holden Nielsen, independent, I don't think he ever published it.
He's talking about God, I think.
What?
Is it God?
It's God.
Yes.
Full of, unsubstantiated.
But the interesting thing is that this argument convinces some people. Okay, and therefore, to me, okay, this is a thought experiment.
But the argument has to be solid. I can write, and I can conclude anything by unsolid arguments, right?
This is a philosophical thought.
Yes, there is a difference.
There is a distinction between philosophical thought experiment and a scientific thought.
Okay, so if I'm not allowed to that, Sabina's saying let's talk about Boltzmann brains, okay?
I've heard discussion about the doomsday argument. I don't want to hear
With Boltzmann brains has the same logical structure, okay? Consider that that there really is a cosmological constant, okay? Then the universe will eventually go into a de Sitter expansion, and everything will die except there'll be a small temperature, and the universe will go on for an infinite amount of time into the future in a de Sitter expansion. Or if you believe in eternal inflation, almost all the universe is eternally in a de Sitter expansion, just the temperature is different. It doesn't matter, okay? So almost all the universe is in a thermal ensemble, okay, at some temperature. In that thermal ensemble, there's a finite probability per unit time and per unit space volume that there exists by a thermal fluctuation a brain. And that is BRAIN, not the string theory brain. And therefore, okay, if we think about instances of brains thinking thoughts, okay, there will be those in the history of the universe in which those brains are the result of biological evolution, like our cells believe ourselves to be, and there will be all the others which are the result of the formation of the brain by momentary fluctuation. And according to what most cosmologists believe, the second will be vastly more numerous than the first. According to what's now standard textbook, lambda CDM cosmology with inflation, okay, it's a slam dunk case that there will be many more brains in the world which appear as statistical fluctuations than that are the result of biological evolution. So we are brains, okay, and we are not the typical case. So do we conclude from that? So what do we conclude from that? That standard lambda CDM inflation cosmology with inflation is wrong?
Yeah.
I think that is the thought experiment.
But I think this is such a loose way of reasoning.
No,
but the structure is the same.
Let me give you a more solid reasoning just from number theory that will convince you of being very careful. There is a finite number of words in English. It's a very large number, but there's a finite number of words.
So
then there is a finite number of phrases with 50 words or less.
So far.
Yes.
English is always growing.
Okay.
No,
Today's English. Of today's English, it's a finite number of words. There is a finite number of phrases with 50 words or less. Some of these phrases can be used to characterize a number. For example, 143. 143 is 5 words. This is a number characterized by one of these phrases. Therefore, there must be an upper bound to the number of numbers that can be characterized in phrases that are 50 words or less.
Yes.
Let's consider the smallest number that is bigger than this number. So it's the smallest number that is larger than all numbers that can be characterized with 50 words or less.
Right.
Well, that number cannot be characterized with 50 words or less, but I just have characterized it with 15 words or less.
That's a famous
So this is,
paradox.
yes,
So
this is a
that's-
very famous
so
paradox.
that's
And
paradox.
this is the kind of loose
No,
talk that I
but,
can prove anything.
What's loose about
See
it?
any connection.
yeah, but Daniel, to come back to Boltzmann Brain, there are good cosmologists, okay, who worry about this. There are good cosmologists
Well, I'm
who
sorry,
do not
my
believe.
impression
No,
of
no.
good cosmologists has just gone
Are arbitrarily good in terms of what they've done in real substantial, comparing observation with data, who take this seriously, who use it either way. This argument has been used to say inflation cannot be correct.
Look, can I give you a thought experiment which everybody will agree is a good thought experiment, it's in the physics, and it's very elementary, so there will be no question about it.
Can I just come
But
back?
what's the question are we addressing now?
Well, I'm just trying to define what a thought experiment should look like.
You define okay.
Can we just come back to what was the reason why you started saying that?
Yeah, so
anyway? You
let's
wanted
do
to
it.
say something of what experiments do we have to take seriously anyway? What does it mean?
No. So my sense is that there's not just a simple thing of thought experiments or not thought experiments. What seems to me is typical of important thought experiments is that at the time they're controversial. That is now the whole argument is a textbook thing. Now the tower thing is a textbook thing. We go yeah. But the point why they were interesting is that they were hotly debated at the time.
Okay.
And maybe the doomsday argument is not a physical thing, although it's loved by some physicists. But the Boltzmann brain argument there's a literature of several dozen papers about it. It's taken very seriously. Okay, and I think it's a genuine thought experiment in that it points to a reasonable implication of the cosmology that most working cosmologists believe, which seems absurd.
Oh, I just wanted to give a simple example that I think that most people will agree that this is a thought experiment. So we can move from there on. This is. Okay, so most people will know this, but maybe some people won't. So this is the Simon Sevin, British scientist, some 300-400 years ago, I think. And he had a thought experiment for a purpose, and Marx liked it very much. I'm sure you know this one. So he started with inclined planes. Two inclined planes, one is a little larger than the other. Okay? And he used, you know this, right? Okay, so he used two chains like this, connected. And then the question is, this is larger with a slope which is less steep than this one. So three questions. Will the chain remain as it is? Or will it move down this way? Or will it move down that way? Just a thought. I mean, he's not doing an experiment. And the answer he gave is that it will stay just exactly like that. From the reasoning, very simple reasoning, that suppose you complete the chain like this. And there is one assumption involved that there is no perpetual motion. Then it's clear that this original chain will simply remain there. So the point here is that the entire deduction is a physical thought experiment, and the deduction comes simply by reasoning and the simple assumption of no perpetual motion. So these kind of thought experiments do give insight into nature, independently of the theory. There is no theory involved here. Just
Yes, you know things about energy conservation. You know.
No,
things
you
No,
don't
but these
know
are
any of
basic
that.
principles. There is no thermodynamics here.
No thermodynamics. This is several hundred years ago, right? So, and the only assumption, and this was an intuitive assumption. There was no Carnot cycle or anything like that. The intuitive assumption at the time that Stevin made was that there is no perpetual motion. This was just an intuitive assumption because there is no scientific basis for it at that time. But it did give insight into nature. And this was a very, and it was controversial, as you pointed out at the time, because people were not sure that they didn't really immediately accept Sterling's argument. Some people had the intuition that this will go this way or that way, and so on. And then Mach made a point of this experiment and showed that how an empirical knowledge can be gained by a simple thought experiment about nature. This is different in character from the brain data that you
No, but when you go to this regime of quantum gravity or this domain where you don't have, basically your intuitions can run wild, and I guess people are happy that this is the case. Then first, how can you trust your intuitions that you are,
right. So here
you do that, and second, and that connects us maybe to the topic of the panel yesterday about what to sacrifice. If you keep your theory consistent with all you have seen so far, and you keep it in that constraint, and then you try to apply it in domains you haven't tested yet, why would you expect to see different things than you have seen so far? And in that case, what will be the phenomenology of quantum gravity in domains you haven't been tested if everything will be the same?
I would like to present also a thought experiment which has a question that I cannot resolve. And my point is not to resolve it here, but to show, to exemplify that by considering this thought experiment, people may start thinking in different ways about quantum gravity, and they will have to make selections about what they want quantum gravity to do and what they can expect from quantum gravity. So, can I do it?
Yes. This is one.
Normally, one of the things that we believe quantum gravity is going to give us is going to tell us that oh no, but that's where I'm going to build my example. So this is one of the things that we believe quantum gravity should give us is the entropy of a black hole to be equal to area over 4. Okay, so let's see. The example is going to question whether we should believe quantum gravity should always do this, would only sometimes do this. Perhaps quantum gravity has to be very different from what we hope it to be. Now imagine, for example, the following situation. 2 concentric shells made out of reflective material. The inner shell can be turned transparent. How you do that? Well, you take Polaroid material that can be rotated, whose axis can be rotated. And let's fill the cavity in between the two concentric shells with radiation with a given polarization. So when the outside the shell is completely reflective, the inside shell is reflective, unless I change it, rotate the Polaroids, and now things can move. In the middle here, I'm going to put some particle that is going to decay. It's going to decay into left polarized photons or right polarized photons. Well, in general, it's going to decay into a superposition of less polarized photons and left and right polarized photons. Here, at the border, I'm going to put a device that if it detects left polarized photons, it will make the Polaroids rotate. If it detects right polarized photons, it will do nothing. If the photons that are right here are left polarized, then this guy is going to turn transparent, and the radiation is going to start falling in. And this thing has been constructed in such a way that the energy contained in the radiation will cross the Schwarzschild horizon. Can I erase here? So this thing is close to producing a Schwarzschild horizon, so once it starts contracting, it will very rapidly cross horizon. The first thing you can say it's a bad idea is, well, to contain all that radiation, these shells have to be very strong. Perhaps they will not withstand the pressure, but I can always put, some things connecting it to infinity and somebody sustaining them to support the pressure. You put your graduate students. Okay, the point is that if the thing collapses, there is a black hole, but the horizon of the black hole is here. And now let's consider this hypersurface. This hypersurface, as you can see how I have drawn it, is previous to the time where the photons will have a definite polarization. So in that hypersurface, there is no information whatsoever if a black hole will form or not. However, the horizon is already present if the black hole
Which
forms.
horizon are you talking about?
This horizon. This is the horizon.
Event horizon, apparent horizon?
The event horizon. The event horizon.
You're saying that it's teleological.
Of course. It's not only yes, it's teleological. It's teleological, and here you have a situation in which the data at this hypersurface is not sufficient to tell you what is the area of something that is already present in that hypersurface. So, should quantum gravity tell me what is the area of this, the entropy of this black hole horizon? In other words, is quantum gravity supposed to be a canonical theory that assigns a state to every hypersurface, and therefore, given that state, I have the information to compute the entropy and everything? Or should not be a canonical theory whereby it should not be expected to compute the entropy? Or perhaps it should not always give this question. Okay, so I don't want you to answer it now, but I just want to exemplify that by considering something like that, you may decide in which way you want to answer and decide what kind of theory you would like and what type of answer you can expect from your theories.
Does this thought experiment have a name?
Sorry?
Does this thought experiment have a name?
We name it the Schrödinger black hole.
Schrödinger black hole.
Because it's like a Schrödinger cat.
Right.
But the bad thing is it's not dead or alive, it's just a black hole.
So everybody agrees, I guess, that there is a role for thought experiments, especially in the domain of quantum gravity, at least, okay, in that sense of maybe first constraining your theory and making it to be consistent with known principles or demanding consistency from your theory. Second, in classifying which kind of theory you want in broad sense. If you want to be canonical, I guess I don't understand what you mean by that, deterministic?
Well, canonical normally means that you have an hypersurface
yeah.
and you have data on that
Initial
hypersurface.
value problem, and you can predict
and that contains, and you have a Hamiltonian, and then that contains all your theory.
So let me try to maybe sharpen the fourth question, before we go to the last one. So the question for me as a philosopher is interesting is, since we don't have any theory yet, and it's not the case that we are doing a Schrödinger cat or EPR where the theory is there and people just question the completeness of the theory. Here there is no theory on the table. And so the role of thought experiments here, or should, as a philosopher, when I, as an outsider, look at this community and then maybe write papers on it, philosophy of science, are these papers, would these papers be published in a psychological, journals, psychology journals, or is it a matter of psychology, of how you come into your theory, how you theorize, or is it actually a practice, a theoretical practice, which is, well established and well?
What do you mean? There are theories on the table in quantum gravity.
Well, not in the same level as. So basically, I'm saying.
But neither was, say, quantum mechanics.
Well, in 35, where EPR.
No, in 35, yes, but it's saying 1917.
But the function of EPR was to kill the theory, not to construct one.
Yeah, exactly.
But in any case, we're not just reasoning a priori from the uncertainty principle and the formula for the Schwarzschild radius. There are half a dozen rather more or less well-developed approaches None of them is complete.
Okay,
But
that's what I mean.
we're very far from it.
Well,
No, because you know, at least my point of view would be that in many historical episodes there is a rich dialogue with experiment long before the theory is past the stage.
True.
We are handicapped by
Exactly.
only having a paucity of dialogue with experiment, which is what this meeting is about.
Exactly. So well, that I think sharpens my question, because with this I started this panel discussion with lacking any data yet. So
I disagree. I think that Stefano, for example, presented a lot of data. There's a lot of there were a lot of people who I used this construction before, but who were good scientists, who would have not at all been surprised to see evidence for Lorentz violation of the Planck scale, no? And there is 7 or 9 orders of magnitude limits past the Planck scale for deviation from Lorentz invariance. So there's a rich experimental. It's not as rich as we would like, but there are definitely
by data
important
you mean
ideas that are
But you
ruled
mean
out.
constraints, not bounds, no?
Bounds, right? What
So-
do you mean by data?
That's data.
Yeah.
Okay. Okay.
You cannot get away with playing games about gravity being emergent from a system on a fixed lattice the way that you could.
Okay. So your theorizing is also constrained by the bounds that we.
Sure.
Okay.
I think Amit's question was slightly different, if I may.
Mhm.
This is a sort of, you could say, negative data, the bounds. But, for example, in quantum field theory, we had actual positive data, land shift. And that triggered everything, because the whole concentration then meant that there is something, a real signal here, and we could build on it. This data only frustrates people. That there are
But is the question, what's the role of a philosopher of science?
Well, the question is the role of thought experiments in that stage of quantum gravity. Is it more in the domain of giving you intuition to construct the theory, or which is different than, for example, the status of EPR that was trying basically to shatter or to call for the incompleteness of the theory?
So here's what I'm. So sometimes I hear you that you're looking to make this specific episode a general case and draw conclusions about the general case that might be useful for some general schema about how knowledge works. That's what you're doing. I reject it totally. Okay. That is. I think philosophy of science is very useful and philosophy of physics is very useful, but I don't think it's useful to discover general schema by which knowledge is increased. I think that the study of historical examples shows such a diversity and chaos of how people come to progress.
Yeah, I agree. I don't put the history of science as a tool for constraining how you need to think now. I'm just trying to map for myself what's going on in quantum gravity, and what is the role of thought experiments in quantum gravity, given that the data you have is mostly constraining you and not confirming new predictions that you might have. That's all I'm saying.
Well, I would say that what you said that it's constructive is certainly true. I mean, since you were just talking about black holes, an obvious example is maybe black hole evaporation. I mean, nobody has ever seen a black hole evaporating, right? So I would argue that's a thought experiment. And we all know that, well, it's difficult to make sense of it. So it doesn't really work with the theories that we have now, but it's kind of clear that whatever the theory of quantum gravity is that we eventually find has to be able to resolve that problem. So that has certainly stimulated a lot of work. No one can argue if that has been progress, but so that's certainly been very constructive, I would say.
I think philosophy, just to come back to Lee's comment, there is a role here for not the strong role that you may be wanting to have, but
No, I don't
but
think
in
that is a
philosophy, the goal is to understand how science works, and that's a noble goal, I think. It may be wrong-headed, and also in that, most philosophers try to do this by looking at historical examples. Why not look also at the current example, what's going on now? It doesn't hurt. You can't draw strong conclusions from it, but you can learn from it.
So two different things. So one of them is what's the role of philosophers in aiding us in quantum gravity? I think there's a huge role. No, okay, while you bring it up, there's a huge role that almost none of you are doing. Okay, which is no, the philosophers of physics or philosophers of science. Okay, there's taking on the hard conceptual questions that we're stymied by, like is time emergent? You know, there's several people. Faye made a statement she believes in time.
Well, I think
Stefan made a statement, he thinks time is real, everything else is emergent. Other people in the community think time is emergent.
Let me defend my colleagues, and I think there is a lot of literature about quantum gravity and the role of time since like 15 years ago even. So I think philosophers of physics are tagging along the quantum gravity, and maybe they are not tagging along the phenomenology.
No, but I don't want you to be tagging along. I want you to be berating us. What I find interesting is a philosopher who says, look, I come from a tradition whereby, for other reasons, I believe time is real, and this is the challenge if you want to make sense of this. This is the case which has been made against the reality of time in the history of philosophy. Okay.
Yeah, so you are much more a philosopher. You are much more a philosopher than most philosophers of physics.
Well, I have more ambition for philosophy than they do.
I think you want another Mark to come up and tell us.
To challenge us, not tell us, but to challenge us.
So
I think that we don't need people tagging along saying, you know, trying to make sense of the nonsense we do. We need a challenge. You know, what's at stake is time real or is time emergent? Okay, it can't be in the highlight of when this is resolved. It will be obvious conceptually that one of them was ridiculous and the other was sensible. Okay.
Yeah, well, this is a more general question about what makes a problem metaphysical or physical. So many problems that were considered metaphysics were eventually turned out to be physics when science got a grip on them. And the question of, you know, A theory or B theory or presentism or the block universe, these questions might become, again, physical question. So far, they are mostly metaphysics. And I agree that they are being the issue of metaphysicians and not philosophers of physics for a long time. And that I agree. No, my point was only basically maybe just to summarize it and then move to the last question and then we can go away. Is that, you know, looking at this community and seeing this theorizing that is taking place. I think that thought experiments have a big room here in doing that. I would like to see more of them in this community.
But I mean, last discussion we saw between Lee and Sabina is kind of a thought experiment,
yes.
Right?
Well, she will claim that it can be now observed. So.
I think it's a real experiment.
Actually, I'm claiming that for that reason it cannot be observed.
Okay, so let me
be
just.
Nice if it were a thought experiment.
So let's maybe be more concrete. For example, in your paper, how much rigor and consistency you need to invoke in a thought experiment in order to make it stick? Given that, of course, nobody will going to perform it, or is it just a matter of convincing other people, or you have your experimentalists have their sigmas? What kind of sigmas do you have in a thought experiment?
Well, so on the matter of consistency, I mean, if it comes to logical consistency, that's essential. You can make any argument if it's not logically consistent.
Consistent with non-physical principles, I mean.
Non-physical
No, with non-physical principles that you...
Non-physical
yeah.
principles. Well, certainly it has to be in agreement with non-physical principles. I kind of interpreted the question a little bit different, like how many details do you have to take care of? And that's, of course, an excellent question because, I mean, no conclusion is ever better than the assumption that you made. So you have to be, I mean, I've tried to be very careful about the assumption that I made to state them all, and Nina's point of view that I didn't mention, but that's the way it goes. And then you kind of notice that there are a lot of things that you don't really have to think about, like all the details of the detector, for example. Or what's the measurement uncertainty of your detector? Is it in some cases it's relevant, and in other cases it's not relevant? And then there are questions of whether the experiment is feasible. And these are typically things that somebody proposes a thought experiment for something, and then somebody else comes up and says, oh, you can actually not build the detector. So that's certainly a point where you could say, well, the rigor was not enough because they have forgotten something. So I'm not sure there's an easy answer to this, right? It has to be as rigorous as it has to be, but there will always be people looking for the holes in your argument.
I think it depends on the thought experiment, or rather specific physical situation that one is concerned about, how much rigor you need. Because the goal of the thought experiment, independently of our discussion, is to look at the logical extremes of the situation and see whether things hold on or they break down. And in some cases, concrete cases like yours, you have to worry, you may or may not have to worry about the details, but in other cases it's irrelevant. Like in Stavin's case, you didn't need any other details apart from what he had. It's a clear-cut logical argument. So it depends on the situation.
Any more comments, questions, answers?
Well, maybe I can ask a question that kind of came up a few times about what we actually mean with an experiment being practically feasible. Like I said earlier, that there's the question: could you actually detect a single graviton? What would you have to do to this? To do
Get
this?
funding.
Huh?
Get funding.
Well, I'm not talking about gravitational waves. I'm talking about gravitons. So leaving aside, TV state gravity, blah blah blah, and funding for the LHC was quite a lot. So I probably wouldn't get that much together. But consider you have an experiment, but it takes like 100 billion years to do it. Is that a realistic experiment? Is that something that we actually have to talk about? So in that sense, does the supergraviton actually exist?
Well,
I mean,
it's a thought
it's the same
experiment.
question with the
If it's a
Boltzmann
thought experiment,
waves, right?
if it's a thought experiment that is going to show internal contradiction of your theory, I think it's fine.
But the question is, do I have to worry about it? Like it's the thing with the Boltzmann waves, right?
So
in the eternal future,
We live in the era of
Boltzmann
reason.
waves are back.
If the theory is logically not consistent, then you
let me give a precise example of exactly that question. There is a priori argument for the existence of photons, which is the ultraviolet catastrophe. You construct a box with conducting walls. You heat up the walls. They radiate electromagnetic radiation. You can show that under the classical theory of if you try to apply thermodynamics to the classical theory of electromagnetic radiation, there's no equilibrium.
That's Einstein.
What?
That's what he.
Right. Well, this is Planck, Planck, and then Einstein and friends, Ehrenfest and so forth. So there is an argument to the existence of photons from the existence of thermal equilibrium of radiation equilibrium with matter, even without an observation. And then, of course, that made predictions. The observations were done. But one can ask, following what Sabinas is suggesting, could one do the same thing with gravitational radiation? Could we not make an argument of the same kind, utilize the ultraviolet catastrophe, and convince ourselves that gravitons must exist? And it's interesting. If you try to follow it down, you find something very interesting, whose significance I think I'm confused about. What you find is that you can't build conducting walls for gravitational radiation even classically. That is, you can show, and this was shown first by Freeman Dyson, you can show that there's no material that you can construct that satisfies that the speed of sound is less than the speed of light, and no no region of it is within its own Schwarzschild radius, and the energy density is positive, and that's enough to show that the attenuation length for a gravitational wave traveling through that material is always larger than the distance it has to travel through that material. So in fact, you cannot, if you satisfy those reasonable assumptions, you cannot make the ultraviolet catastrophe occur for gravitational radiation because you can't keep it confined for long enough to reach equilibrium to make the existence of gravitons necessary. Okay. And this argument has been known for a long time from different people, and yet almost nobody has drawn the obvious conclusion from it. Okay, which is that maybe there are no gravitons.
But because maybe the detection of the photon was not done using the original
argument. But nonetheless, okay, it's very intriguing to ask, is this a case, this is a clear difference between electromagnetism and gravity related to thermodynamics. As Stefano said, there's a very deep thought of a connection between gravity and thermodynamics. Here's a very clear difference between them. Okay, and it sure is suggestive, but to my knowledge, nobody has been able to take that. Anywhere. And there is a thought experiment playing a role, pointing in the direction that very few people would, at least maybe now with emergent gravity is changing, but very few people would have imagined that, would have wanted to take advantage of the open door that maybe physics can be consistent without gravitons.
Well, the holographic principle of the entropic force of Berlin, if gravity is emergent, then you don't need a particle, you don't need a carrier. If gravity is not a fundamental force, then you don't need the carrier. So there is, unfortunately, for the electromagnetism, I think we had sufficient experimental evidence that the electromagnetism and photons exist, and then you could draw conclusions about the ultraviolet catastrophe and whatever, because you are applying laws that you have tested. For gravitons, you don't have any evidence that they exist.
But let me push it even bit stronger. Okay, before there was evidence for photons, before the Compton effect and the photoelectric effect, okay, there was the black body spectrum, which was observed.
That's right. That's right.
Okay, and in hindsight, okay, is there any version of electromagnetism which is consistent with the Planck distribution, which does not have photons? No. Okay. So in fact, that's all that was needed to make an open and shut case that there were photons was the Planck distribution, and indeed Einstein reasoned from that.
But precisely, once we discovered gravitational radiation, suppose that there was an evidence, suppose that we have seen gravitational waves, then we would apply that argument that since we see the gravitational, the analog, if there is such a thing, then you could draw a conclusion about the existence.
No, but only if it's thermal. So
only if it's thermal. I agree.
A related argument shows that nothing in the history of the universe, as long as the positive energy principle is satisfied for matter, that nothing in the history of the universe could thermalize gravitational radiation. Yes. So so if gravitational radiation, cosmological background gravitational radiation were observed, which was thermal, it would be deeply puzzling.
Yes.
Because there's no mechanism that could possibly have thermalized it.
And then it would probably point towards non-fundamental nature of gravity.
I don't know what it would point to.
Okay.
This is an argument that Grisham made a long time ago.
But certainly not the gravitons that we expect to have.
When people were thinking about black body radiation, nobody made the argument that, which I imagine is very natural, that very high frequency things will not be confined within this box. That matter perhaps was not able to confine high, sufficiently high frequency photons, and then you would exit.
No, because I think they knew experimentally that in the frequency range that they saw the peak of the black body, they knew that they had mirrors for.
Oh, okay. So it was not the catastrophe, then it was already the spectrum.
Yeah.
Because the catastrophe you needed to integrate all the way to infinity.
Right. Well,
the catastrophe comes from the theory.
Right. Yeah, but I imagine what I'm saying is a way out of the catastrophe is to say, photons with sufficiently high energy escapes the box.
But if you have the spectrum, it's enough.
No, if you have the spectrum,
away from the
if you have the spectrum,
or the constraint.
That's why you lack it. I believe for gravitons, it is a distinct lack of any any sort of experimental evidence, if you think about it, direct. I mean, the only indirect evidence that there are gravitational waves, and that's what I'm inclined personally to think that there might be something such as gravity, is the gravitational impulsion, the slowing down of the.
Why do you think that this is pushing for gravitons? It's just a push
No,
for
gravitational waves.
No, but you just okay.
Gravitational waves, I said. Of course, if you get gravitational waves, then your logic, your intuition and experience applies, and you say, then I might have an analogy. But that doesn't point towards the existence of gravity. But the gravitational pulses shows the change of frequency, and they measure it. They got a Nobel Prize, so they must be, being in this country, this must be solid experimental evidence. So this points out that there is probably gravitational radiation. Now, the question is, which I'm posing to this audience and to our philosophers, that's what the philosophers are. If there is gravitational radiation, is there any argument that it shouldn't be like electromagnetism? It's probably the kind of radiation. If it is thermal, as Lee pointed out, then probably there is a problem. If it is not thermal, then...
So why the strong... Sorry, my question was for you.
No, go ahead, no.
Why the strong equivalence principle is not a valid reason for...
Because it may not be valid.
I'm sorry?
Because it may not be valid.
That's right, but at least we are
But
talking
that's not
about...
an evidence that there exists gravitons. No, the question, as far as I understood, is whether there exists gravitons. A strong equivalence principle does not say that you have gravitons, i.e. particle...
No, it said exactly the opposite. It says that even the self-gravity of whatever it is, gravitational wave or whatever, must fall at the same rate. So there is no reason to assume that it's just some sort of a particle just accumulating in some flat background or something. I'm not saying that there is strong evidence against it, but I'm saying that,
what's your point? You say?
But your point was that since we have a gravitational radiation, we have, let's say we had it. I mean, this
Okay,
is
but
very
you assume that we have- okay, fine.
partial evidence convinces me that there are gravitational.
Okay.
That's fine.
Which
But
we
that
don't
doesn't
have at the
mean
moment.
that doesn't necessarily mean that we have gravitons. Now, your question was: is there any reason to doubt that this does not lead to graviton immediately?
Yes.
Well, I think that strong equivalence principle, if it holds true, and we know experimentally it holds true to enormous accuracy, gives us enough reason to doubt that. That it's not straightforward that gravitational radiation simply immediately means that there are gravitons. That's what I'm saying.
But moreover, you can imagine these as waves. You can always quantize them. This is not telling you that these are not phonons like.
That's right.
Yeah, exactly.
That's right.
Right.
I mean, it's not proving it. I have a comment regarding gravitational radiation. I think that has not been sufficiently appreciated. One of the inputs that is coming from this space-time thermodynamics approach à la Jacobson. You see, for people that is not familiar with this, basically he's starting imposing the Clausius relation to a local Rindler horizon, having flux on matter, and check basically the imposing the Clausius relation, and basically using, if you like, from the change in the area of the horizon, associating that to the change in the entropy. And you find out, in general, that the imposing the Clausius gives you something which is not the Einstein equation. It has Spurious terms, which are allowed simply by the structure. You are just assuming local Lorentz invariant, or if you like, you are just assuming the strong equivalence principle, because you are computing the entropy as entanglement entropy and putting a cutoff which is space-time independent. Given that the cutoff is supposed to be of gravitational origin, it's the only place where gravity enters in this argument directly. The idea, this cutoff is then related to the Newton constant. You assume that is a constant. Now, what is this Spurious term? It's something that is related to the shear of the horizon. And it is something that you have to put as unbalanced set. It's basically, you have to admit that you are not doing equilibrium thermodynamics. There is something that is non-equilibrium. And this is exactly the kind of terms in an equilibrium thermodynamics that you have due to dissipation by heat. And this term comes out to be the Hartley-Hawking tidality. That means it's the term that in black hole physics, and here we are talking about a local Rindler horizon, it's totally, in black hole physics is associated to the dissipation of perturbation of the gravitational wave. So So what is telling you is that this is what we call gravitational radiation. It's not waves on the space-time. They're in the space-time. It's like doing this. There is no local object that you... It's obvious that there is no covariantly conserved stress energy times. There isn't any wave that is propagated. It's just like heating a table somewhere and then putting a thermometer. You can transfer energy this way, but it's not something that travels as a wave on the space-time. It's really something inside the space. You see, and the point is that, so even this intuition that sometimes we have of gravitational radiation, let's say a wave, a quantized, I don't know, it seems to me that this is teaching us something deep about the nature of the gravitational degrees of freedom. Note that these things, this is my last point, can be generalized to scalar tensor theory, to higher curvature theory of gravity. You can do it for f of r, for example. You find out that, as you should expect, there is a scalar degrees of freedom. You have basically a scalar Hartley-Hawking tidal-heating term. There is the bulk viscosity. Before you have a kind of shear viscosity term. Now you have a bulk viscosity term. This is associated with the fact that you are propagating scalar degrees of freedom in your gravitational theory. Yeah. So it's really different. The intuition, the name gravitational waves, I'm tending to think that it may be a bit misleading in a certain sense, if you see it in this way.
Well, if you think in terms of electromagnetic waves.
Let me just say something. You asked the philosopher what I think about electromagnetic. I don't have any stakes in this, but again, I think taking what Lee said about the difference between the two types of thought experiments, between gravity and electromagnetism, and you all talk about thermodynamics of black holes, maybe you take thermodynamics too seriously. I have a colleague, philosopher, that wrote a paper taking thermodynamics too seriously when you apply it to these objects, when we know, first of all, that it's not a fundamental theory, in a sense that it's a kind of statistical generalization, and we must be, I think, very cautious about analogies between one theory to another.
So, analogies are using a thermodynamic.
Well, they're using a structure.
But they're using the Clausius relation and conservation of energy. And you're using that there is the strong equivalence principle, what I just told you. These are the three ingredients, and you derive the full gravitational theory, full GR, plus. Not correction, it's not the correction to the waves. You have the Einstein equation and you have another level which is related to the Wright tensor and which is related to what we call gravitational radiation. It's very strong. I mean, it tells you that there is something, it's the nature of the theories, it's pointing out to something deep about the nature of the theory you're playing with.
But just to play the devil's advocate, I agree a little bit with you. I mean, and this is something that I'm very interested with. I've discussed quite a bit with Ted and all these ideas. I find it very interesting. But nevertheless, I see a little bit the point in what he's saying, in the sense that if you compare with our usual understanding of thermodynamics, statistical mechanics, this notion of entropy, at the thermodynamic level, also in statistical mechanics, as a counting of microstates. We have a clear understanding of what we mean by entropy as a counting of microstates in statistical mechanics. This is something that we still don't understand in the context of black holes, or clearly also in this context of emergent gravity. So we have this idea, this notion, for instance, of some kind of entanglement entropy, for instance, this intuition that you have in black holes, or in your interpretation in this context. But there's no clear understanding, I believe, of how that could be related to some kind of counting of microstates, which is the usual interpretation in the context of
that's a bit away of what I asked.
But
I asked you to see gravitational radiation, what can we conclude?
I'm just trying to interpret what I think he was saying.
But this doesn't tell you that you shouldn't take very seriously the fact that thermodynamics intuition is driving you to a theory, to the full-fledged theory, including a very deep interpretation of what we call gravitation.
I'm not saying that you should stop that line of thought.
It cannot be a confidence.
I'm not saying you should stop that line.
Okay. I think for the general good, we will finish the discussion now. I thank everybody in the panel and the organizer, and thank you very much.